Hi, we are going to be talking about the hydrogenic atom. So the hydrogenic atom is the system that we use to start to build more complex atoms, represent more complex atoms quantum mechanically. The cat just joined me. Hi, kitty. So one of the things I want to talk about is how we take the systems that we've built thus far, namely this particle in a sphere, and we build it towards adding now a proton to the center. Okay, so we have our spherical system, but now we have a proton, which means we have a positive and a negative interacting with one another, which means we have a Coulombic potential. Coulombic, it's exciting. Okay, so where did my notes go? It's just like class, I lose my notes all the time. Okay, so notice I've got a Z here. This is the number of protons multiplied by the fundamental charge, and there's a positive right there to denote that this is always going to be a positive value because it's, well, protons. Okay. Name of the game, H psi equals E psi. Now we have the problem of figuring out what is psi. But actually, before we do that, let's look at the Hamiltonian. So as you change your system, your Hamiltonian is going to change. So particle in a box Hamiltonian is different than the harmonic oscillator Hamiltonian, is different than the particle in a sphere Hamiltonian. Now we are adding in the potential energy associated with this electron coulombically interacting with this proton. So Hamiltonian is going to be minus h bar squared over 2 mu. Note, mu is the reduced mass. And note, most of the time, the electron is going to be so teeny tiny in comparison to the nucleus that it'll reduce to the mass of the nucleus. It'll reduce to the mass of the electron because the mass of the nucleus is so small. So if you were actually, let me show you that real quick. If you were to say, so this is mass, nucleus, electron, this also equals, so if I were to say 1 over mu and take the inverse of this, as well as manipulate it by multiplying by the most common denominator, then you get 1 over, oops, mass of the electron plus 1 over mass of the nucleus, which is approximately equal to 1 over mass of the electron. Because this is so massive, this is practically 0 in comparison to the mass of the electron. Okay, ask yourself why that is. Not the difference in the mass of the electron and neutron, or electron and nucleus, but how you got from this point to this point. Okay. So Hamiltonian kinetic energy operator plus potential. Think about what the potential is going to be here. So we're going to add, and I'm going to explicitly say I'm going to add a negative z e squared over 4 pi epsilon 0 r. Negative to note that it's a attractive force in between the electron and the nucleus. You've got a negative force is going to be one that's drawing you forward versus pushing you away. Now you've got e squared over 4 pi epsilon r, so there's your q squared over r, there's Coulombic. This is a conversion factor. Epsilon naught is the permittivity of free space. It's how well electric fields can permeate through a material. Also known as the dielectric constant. If you have a material present, if you have vacuum, it's epsilon 0. Okay, hopefully all your physics is coming back. Cool, okay. Now, let's see what else. So this is my Hamiltonian. I'll take this and stick it in this equation. But then what is my wave function? Everyone following me so far? Pause, write down a question if you need me. Okay, so psi is normally x, y, and z, but we want to convert this to psi as a function of r, theta, and phi. Now, we've already done this for the spherical system where we just have a particle bound to a sphere. But now what we want to do is we want to incorporate this r. So via separation of variables, this became the spherical harmonic. Let's see, it's m sub l and L of theta and phi But now we're going to multiply it by what's called the radial function. Cool? Everyone follow? So we kept R constant, and we just looked at theta and phi dependence, and we got our spherical harmonic. Well, now we're going to join back in R, which is going to be the radial component. Okay, and so we know, and I say we know, excuse me, because of previous chapters, and because our friends, the physicists, have solved this for us. We're chemists now. We don't care necessarily where these come from. We want to know how to use them to answer the question of how do we talk to molecules. Oh, coffee is wonderful. Okay, so we know that this breaks up into, and I'm just going to move R to the front. So there's our theta angle. There's our big phi angle. And so now we've got our theta and phi. Theta, the function, is represented by a constant A multiplied by the Laguerre polynomial. I'm sorry, Legendre polynomial. You go to the table, you look up the polynomial associated with the L and M sub L values that you're wanting, and you plug it in, and you have your function. Cool, just like the Hermite polynomials, like you saw for the harmonic oscillator. Okay. B is A e to the I M sub L phi. Cool, I like that. Question now, R equals what? Okay. This is the radial component of the wave function. This is the thing. Okay, so you know that the 1s orbital has a particular shape. What is that shape? 2s. 3s. Cool. Let's look at the 3s. If you were to plot the 3s orbital as a probability, think about what it would look like. Okay, so you're going to have something that looks like this. Whoops, I got it backwards. So probability as a function of R, this is distance from the nucleus. So here's our nucleus, nuke. Okay, so 0 here, right? Now imagine that in 3 dimensions. Okay, you've got your sphere, got your nucleus, and then as you're going out, there's going to be 1s disappears, 2s disappears, 3s disappears. And I say disappears as in that's where the angular node is. So there's an encased sphere. Probability decreases, a larger one decreases, larger one decreases. So now, so this is for the 3s. Imagine the 3p. Go team. So we now have to have 0 at the boundary, or 0 at the nucleus, because the electron's not existing at the nucleus. We have to have 0 far away from the nucleus, because again, you rip the electron off of the nucleus, it's no longer attached to the nucleus. But then there's also these radial nodes. So we have these 3 components that we need to take into account to build a function that will give us an R that satisfies all of now the boundary conditions. And when you multiply it by these 2 functions, gives you a wave function that represents the system such that when you take the Hamiltonian operator operating on it, it gives you energies that match the atomic spectra. Quantum is beautiful, isn't it? Okay, so you see where we're going? I'm going to give you the 3 things that you multiply together to give you R. I will give you R, and then we'll start playing with the energies. Cool.